Okay. In our paper we have, sorry, in the note page, you actually have the list of the observed. I'm going to jump to the calculator and talk about how to input this stuff first, and then we'll come back in and do the formal write-up on how one generates this. Okay, so this is a new place in the calculator that we haven't had to play with before, but this is how we have to input these chi-square data. And what we're going to do is we're going to go to the matrix menu. So you want to hit second, looks like x to the negative 1, and this is going to pull up a list of matrices. Kind of like stat edit, we want to go over to matrix edit, and we're going to input something in for matrix A. So I'm going to hit enter, and it's going to ask me what are the dimensions of the matrix. Okay, the nice thing is I don't have to input the totals, I just need to put in the observed, and the calculator will actually figure out for me what the expected is based on what the observed is. It'll reorganize the totals and kind of do that underneath the surface for us. So I need to input that row of number, or that column of numbers, that 100, 150, and 50, and then I need to do the second column of 50, 125, and 25. Okay, so when you input matrices, you're inputting in a number that represents the number of rows by the number of columns. So we have cut A, cut B, and cut C. So there are 3 rows. And then we have north and south, so there are 2 columns. And notice it generates a list of some empty spots for me to fill in just those 6 numbers. So I'm going to input in just the observed, the 100, which I have in there oddly enough. Just type that in again. And then when I hit enter, it's going to move it over to the next spot in the first row. And so I just want to input the 50. And I'm not worrying about the totals at all. It's a nice thing about this. I don't have to do the totals, just the observed. So then row 2, I want the 150. And I want the 125. And then for row 3, I want the 50. And I want the 25. Okay? Alright, so that's kind of the new thing. Then we're actually going to go through and we're going to do the chi-square test. I'll do the formal write-up here in a moment so you can see the assumptions and setting all the fun stuff up. But let's go to stat and then arrow over to test. And this time we want just the chi-square test. We don't want goodness of fit. So we're going to keep arrowing down until I see just the chi-square. So let me kind of show you that. Goodness of fit shows up right below it on mine. Okay, now the calculator is going to ask me where did I put the observed. Now we typed it in matrix A, but notice I didn't touch matrix B. Okay, and that's the nice thing about this. The calculator is telling me that it will actually figure out the expected for me, and it will put the expected matrix into a matrix called B. Okay. So I just need to make sure that I have my observed in. I'll kind of show you what all that looks like here in a moment. So then I'm going to hit calculate. It does all that fun stuff for us, and then this would be the chi-square, the 7.57, and the p-value, which is 0.0226. Okay. Now let me go back to the matrix menu and let me show you that it actually did figure out the expected for us, that we didn't have to do, and we didn't have to type that in. So if I go to second matrix, notice I have this B matrix that has the same dimensions as the A matrix. So I can arrow down or just hotkey it, hit 2, and when I hit enter, it just says B. I hit enter again. It'll actually pull up that matrix that we generated by hand using that row times column divided by total method. Okay, so the nice thing is all you need is your observed, and your calculator will generate the expected for you, and then you can use that as part of your assumptions. Okay, so let's go back and let's do the formal write-up on this particular problem. Okay, so our assumptions is that we have a random sample, and it was stated in the problem, and we need to confirm or demonstrate that our expected counts are greater than 5, And so that's where we're going to pull that matrix B from the calculator and put it in our assumptions. I know it sounds kind of backwards because we calculated the p-value first, and now we're going back in and putting the formal, this is what we expect to see. Honestly, what we're doing is we're sort of taking advantage of the fact that the calculator's got this nice built-in shortcut for us. Otherwise, we would have to deduce the expected counts before we could even proceed with the test. So in that sense, we're kind of working a little backwards here. But once we've got our assumptions set up, then we're going to set up our hypothesis statement. So our null is that geographic region and beef preference are independent. In other words, it doesn't matter where you live, everybody likes meat the same, and geographic region and beef preference are dependent is the alternative. So we suspect we can gather evidence to suggest that where you live defines the type of meat you eat. Then I can set up the calculation part, and that's just setting up our formula. And you remember those numbers we saw from the calculator. So that 7.56 is our actual chi-square, and then the p-value that represents that would be 0.0226. Again, notice we didn't type in degrees of freedom, but if I cover up one row and one column, that just leaves two numbers left over. So that process does work for us. Alright, now what? Well, our p-value is clearly smaller than alpha. 2% is a lot less than 5%. We get excited about that. That means we were successful in gathering evidence. So since p-value is less than alpha, I reject the null. There is sufficient evidence to suggest the geographic region and beef preference are dependent. Not a shock to us Texans. Alright, the last chi-square test we're going to talk about is the hard one to say, the chi-square test for homogeneity. This is used for a single categorical variable from two or more independent samples. So the independence test was one sample with several categories. This is one category with several samples, if that makes sense. And we use this test to determine whether the populations are homogeneous or essentially are the same. The nice thing about this particular test is the assumptions and the formula are all the same. Expected counts and degrees of freedom are all the same. The only thing we have to change, literally the only thing we have to change when we do this particular test is the hypothesis statement. Even the calculations on how we do it are the same. Okay, so our hypothesis statement for homogeneity test is the proportions for the two or more distributions are the same. Thus homogeneity means same or not same. And then your alternative is that the proportions for the distributions are different. Okay, and again we're doing this in context. Okay, the following data is on drinking behavior for independently chosen random samples of male and female students. Does there appear to be a gender difference with respect to drinking behavior? In other words, do men and women drink differently at different amounts, I guess. Alright, so let me pull up the data and then we'll type it in the calculator. Okay, so we're going to turn our calculator on and we're going to go input this observed matrix into our calculator and let it do the work to figure out the expected and the p-value and all that fun stuff. So we're going to go to second matrix. I've already got stuff typed in from before, but that's okay. We're going to type over it. And I want to go to edit and then let's kind of figure out what this is. So it's row versus column. So I've got 1, 2, 3, 4 rows. Again, I'm not doing the totals, I'm just doing the observations. And then men and women would be 2 columns. So it's a 4 by 2. Okay? And then I just need to type in all those numbers. So 140, 186, 478, 661, 63, 16. Oops, I missed a row. Oh no. Sorry if you're freaking out at home. That would be 63 and 16. Okay, so I'm going to arrow back in and change where I messed up. So it needs to be 300 in that column and 173 there. So if you mess up, just type over it. Make sure I didn't make any other mistakes. Okay, so we look good. So there's my observed matrix. And then I want to go to the test. So stat, arrow over to test. And I want to look for chi-square. Okay, now again, I didn't type in my observed. I'm going to let the calculator do it for me. So it's observed, and it's going to throw out the expected into matrix B, and then arrow down to calculate. And so it does some thinking for me, and I see a very interesting number. So I got a chi-square of 96, which is really high. And then I have 8.6 e to the negative 21. Let me just clarify what that means real quick. 8.6 e to the negative 21. E to the negative 21 means 0.0000, 21 zeros in a row, 20 zeros in a row actually. And then we hit 867. So as far as we can tell, it's 0, which means there's definitely a difference between gender and drinking level. So kind of go back in here. Degrees of freedom, just kind of remind us of how they did that. So if we cover up one row and cover up one column, then it leaves us with 3 numbers total. Okay, so you want to kind of write those numbers down for a second. Let's go figure out the expected numbers. So we'll go back to the matrix, so second matrix. This time I want to look at matrix B and hit enter, and then those numbers are the expected. So one of our assumptions is we're going to have to show that the expected counts are greater than or equal to 5. So I want to just do a quick jot down of those numbers for the assumptions. Okay, and so let's go through and do the formal write-up with all the fancy language and the calculations and the things that would be expected to be done on a test. Okay, so formal write-up. We need to check our assumptions. So our assumptions are that we have a random sample of students stated in the problem. We need to demonstrate that the expected counts are greater than 5, so I physically need to write down that expected count matrix that the calculator did for us. Then we need our null and alternative. So the null would be the proportion of drinking behaviors is the same for female and male students, and the alternative is that at least one proportion of the drinking behavior is different for female and male. And then we'll set up our chi-square and then summarize what we got for a p-value. And so that 0.000 e to the negative 21, that's about as close to 0 as you can ever get. Anyways, so our p-value is clearly less than alpha. So there is, so p-value is less than alpha, I reject the null. There is sufficient evidence to suggest that drinking behavior is not the same for female and male students. Hopefully not a surprise there.